Yes, thank you. And thank you very much for the invitation to speak today. I'd also like to acknowledge my collaborators on this talk. One second. There we go. So, of course, this is joint work with my supervisor at SFU, Ben Adcock, and his two students, Juan Cardenas and Sebastian Moraga, and then also with Simone Bujapaya at Concordia University, my advisor, Clayton Webster at University of Texas at the Odin Institute, Huang Tran at Oak Ridge National Laboratory, and Abdullah Chikifa at Mohammed VI Polytechnic University. So this is going to highlight a lot of work over the last, I'd say, 5 or 6 years on developing methods for sparse approximation of parameterized PDEs, but it's also going to highlight some more recent work on neural network approximation of these problems. So the main motivation or the goal in this talk is we're going to compute an approximation to a function f from u to v. So the mapping, we want to approximate the mapping that takes y to f of y, where u is a subset of Rd. Typically d is much larger than 1, or it could possibly be infinity. And we're going to do this from noisy samples di equal f of yi plus ni. In some space VH. So our function takes values in a space V, and then later we're gonna try to approximate it with data from VH. So some settings in the assumptions, informal assumptions. The function that we're gonna approximate is smooth. So for example, it's holomorphic with respect to the variables y. It takes values in an infinite dimensional Hilbert or Banach space V. Typically in these problems, the UQ problems that we're going to talk about, sampling is generally expensive. So for example, each sample requires solving a PDE. So obviously we want to minimize the number of times we want to do that. And then of course we have some noise, and which could come from the measurements or the discretization of V to VH. And then finally, we're often, but not always, free to choose the sampling points yi. In the majority of this talk, we'll talk about just sampling from some probability measure, but then at the end of the talk, I may present some more recent works on adaptive sampling schemes using neural networks. So the main challenge here, of course, is the curse of dimensionality. These problems are typically very high dimensional, and so we need efficient algorithms that can actually compute these approximations. The parametric PDE black box model motivation is assume that we have some parameterized PDE of the form L sub x of u of x and y is equal to 0, subject to some suitable boundary conditions. And then we want to approximate the solution to this PDE from sample data yi and u of yi, where here y is a parameter variable, and it's in the input space, and then x is the spatial or temporal variable of the PDE. L sub x is a differential operator in x, and then v is the actual solution space of the PDE. So for the parameterized elliptic PDE, we have v is equal to h01. The goal here is we want to cheaply approximate a quantity of interest, q of u, so a function of x and y. For example, we could approximate the parametric spatial mean, or we could consider something like the spatial expectation or variance. And of course, there's many different methods for attacking this problem, and those include stochastic Galerkin methods, sparse grid methods, Taylor methods, least squares, and we'll also talk about compressed sensing-based methods in this talk. So the standard setup is here. We're going to assume we have U is the unit hypercube. We have rho, a tensor product probability measure on U. We have an orthonormal polynomial basis of L2. And so these are just formed by taking the product of our one-dimensional basis polynomials. And then we're going to also assume that we have a bounded orthonormal system. So given some multi-index set lambda, that means that there exists a theta greater than or equal to 1, such that if I look at the L infinity norms of all the basis functions, these are all bounded by theta, irrespective of the multi-index nu. So some examples here include the uniform distribution, and this leads, of course, to the Legendre polynomials, and the Chebyshev distribution, of course, that leads to Chebyshev polynomials. And the idea here is that we can expand the function f in L2 by writing it as this series. So you have the sum over nu and 0d, c nu, psi nu, where the c nu's here are nothing more than just the inner product of our function with the basis polynomials. So in the case of a parameterized PDE, these coefficients are actually elements of the space B. So the question you might ask is, why would we consider orthonormal polynomials? Well, we have these nice results that say that the smoothness of the function implies fast decay of the coefficient C in the vector taken by taking those coefficients C nu and grouping them in a vector. And so if I let psi nu be an orthonormal family of Legendre polynomials, then the coefficients can be bounded by like beta to the beta to the nu over nu factorial times the partial derivatives of f in L infinity with beta greater than 0. So the first step, of course, is to truncate the function f in some basis selected a priori, indexed by the multi-index set lambda. And then we have these coefficients c nu in the polynomial approximation case. These are actually scalar valued coefficients, and so we can just directly try to approximate them using some methods. Here, n is going to be the cardinality of the basis that we select. Some common isotropic choices of lambda include the tensor products, total degree, hyperbolic cross, and Smolniak sets. But the main takeaway is that algorithm costs here scale poorly with the dimension. N grows quickly with D for many of these choices. And lambda, each choice of lambda is going to introduce what's called a truncation error. So we have f minus f lambda, which is nothing more than the sum over coefficients not in lambda, c nu, psi nu in L2, or c sub lambda complement in L2. So the optimal choice, of course, is to choose lambda sub s corresponding to the s most effective indices to minimize this truncation error, but this is unknown a priori in general. So the smoothness assumption that we're going to work with is that there exists typically unknown rho with rho greater than 1 in each component, such that the function f is holomorphic with respect to y in a Bernstein polyellipse. And there's two different cases that we could work with. The first one is we actually have known anisotropy, so we can actually construct the polynomial space P lambda, perhaps depending on rho, that actually exploits the anisotropy in the problem, and this will lead to near optimal least squares approximations. The second, more challenging case is when we have hidden anisotropy. So here's where the unknown values rho j could differ in scale according to the smoothness in each coordinate direction. And this leads to a wasted effort for isotropic approximations. So we want to avoid the second scenario, wasting effort as much as possible. Some benchmark approximation results say that if I look at that best S term approximation, I'm going to get an algebraic rate of convergence under this assumption, even when I have infinite dimensional problem. And then we can also, using bounds of the coefficients C nu, we can show things like quasi-optimal S-term approximation rates. These lead to exponential rates of convergence with explicit parameter rho and D dependence. The last 10 years of research, I'd say, has focused on methods to exploit this nonlinear low-dimensional structure. And we'll try to talk about some of those in this talk. So during my PhD studies, I became involved in compressed sensing research. So in compressed sensing, the idea is here we want to find a sparse solution to X of the undetermined system AX equals B, where A is the measurement matrix and B is the data. And the key idea here is that we don't really know where the non-zero entries are in the vector that we're trying to recover. We just know that it's a sparse vector. Of course, this has origins going back to Candes, Romberg, and Tau in 2006 and Donahoe in 2006. And since then, it's been the subject of thousands of papers, dozens of survey articles, and several books. And it also caused an important philosophical shift in how we view the task of reconstruction and inference. So this has applications, of course, in imaging, communications, sonar, signal processing, classification, and tons more. The basic idea, though, if you've heard of compressed sensing, you've seen this before. You're going to solve the underdetermined system via L1 minimization. So, for example, We can consider the basis pursuit problem, where we're going to minimize over vectors z and cn, the one norm of z subject to az is equal to b. So here the support of the vector c is the set SUPP of c sub c. It's the set of nu and lambda such that c nu is not equal to 0. A vector c is called S sparse if for some s in the natural numbers less than or equal to n, the cardinality of the vector. If the L0 norm, which is defined as the cardinality of the support of C, is less than or equal to S. We say that the set of S sparse vectors is denoted by sigma sub S, and then exact recovery via the basis pursuit problem is implied by the following. So this is the restricted isometry property of the matrix A. So a matrix A satisfies the RIP of order S if there exists a delta in 0, 1, such that 1 minus delta times z's 2 norm squared is less than or equal to az 2 norm squared less than or equal to 1 plus delta z 2 norm squared for all z in the set of S sparse vectors sigma sub S. The smallest delta such that this holds is called the restricted isometry constant, or the RIC, and it's denoted delta sub S. And the main rationale for why we consider compressed sensing is that it actually turns out that there's many m by n random matrices that satisfy the RIP of order S with high probability, provided that m scales like S times some polylogarithmic factors in n. So of course, that's all well and good, but in general, we actually have noisy data, and in particular, we actually have we may be operating under the assumption that there's actually some structure in the sparsity of or structure in the coefficients of our signal that we're trying to reconstruct. So for a generic type of structure, we can introduce the so-called weighted L1 version of this problem. So the weighted quadratically constrained basis pursuit problem now replaces the equality constraint az equal b with az minus b, and the 2 norm is less than or equal to eta, which allows us to encounter noise in our measurements and still reconstruct. Of course, the weighted L1 norm of C, the weighted L1 norm of C is the vector C, is the norm 1W, which is defined to be the sum over nu in the multi-index set lambda, W nu times the magnitude of C nu. The weighted cardinality of an index set lambda is defined by the weighted cardinality of lambda with respect to the weight vector W is the sum over nu and lambda W nu squared, where the W again are the weights that we're going to consider in the weighted L1 norm. A vector C is called weighted KW sparse for K greater than or equal to 0 and W strictly greater than 0. If the weighted cardinality of the support of C is less than or equal to K for some K. The set of weighted KW sparse vectors is denoted by sigma sub KW. And then the idea here is that replacing sigma S with sigma KW leads to the so-called weighted RIP. And in fact, if we set W equal to 1 vector and K equals to S, this actually returns us back to the original RIP. So the following theorem establishes the weighted RIP for bounded orthonormal system measurement matrices A. And it says let delta and epsilon be between 0 and 1 and K be greater than 0. And then define A, the measurement matrix, as 1 over square root of m. And then in each component, we have psi nu j evaluated at the point yi. So this is our m by n measurement matrix. And then psi nu are going to be the bounded orthonormal system. And now if W are our weights and W satisfy the bound W nu is greater than or equal to the L infinity norm of the basis function psi nu for all nu and lambda. And then if M is greater than or equal to some constant C times delta to the minus 2 times K times L, where C is universal constant, positive universal constant, and L is equal to this polylogarithmic term here involving K, delta, and N, and epsilon, then with probability at least 1 minus epsilon, the measurement matrix A satisfies the weighted RIP of order KW with weighted restricted isometry constant delta kW less than or equal to delta. And so this version can be found, of course, in my advisor and Ben and Simone's most recent book, but also you can see our previous result from 2017 with Abdella, which establishes the theorem behind this. So now we've talked about weighted approximation. What kind of weights and what kind of structure do we actually want to try to encourage? Well, we're dealing with smooth functions, so it's important to introduce the idea of a lower set. So an index set delta is called a lower set, also called downward closed set. If and only if nu in delta and mu less than or equal to nu implies that mu is also in delta, where mu less than or equal to nu is implied to mean component-wise mu k is less than or equal to nu k for all k between 1 and d. So here, this is an illustration of what I mean by lower set. So on the left, we have a lower set, and then on the right, two examples, or the middle and the right example, we have two sets that are not lower sets, because here this set has this gap right here, and this set here has this hole. So we can't have those kinds of things in lower sets. Quasi-optimal approximations, however, so based on lower sets, you can show exponential rates are often achievable by an approximation f sub s hat, defined as the sum over nu and delta sub s, c nu times psi nu, where delta sub s is a lower set of size s. The main idea is that behind this is that the support of the largest expansion coefficients of smooth functions is approximately lower, and this is motivated by this series of works. You can see here for more details. The way that we're going to actually enforce this in our weighted L1 recovery scheme is we're going to choose these so-called intrinsic weights, i.e. setting W nu is equal to the L infinity norm of psi nu, which in the case of Legendre polynomials, this is the product over I equals 1 up to d of 2 times the square root of 2 times nu I plus 1. And then, of course, we're going to take advantage of the hyperbolic cross as well, because this can be seen as the union of all lower sets of size s. So these two choices are going to help enforce this lower set structure for smooth function approximation. So here, let me show you an example of how this works in practice. So, oh, went too far. Here we go. So here I've got the smooth function e to the minus sum of cosine yi's divided by 8d up at the top. And then you can see in 8 dimensions and 16 dimensions, so each row it corresponds to a different dimension. I've got on the left, the top left, I've got the coefficients of the expansion just plotted in magnitude. And then in the middle, I've got them sorted by magnitude. And on the right, you can see the error of the compressed sensing based approximations based on doing this lower set based L1 structured sparse recovery. And you can see that in particular that when I choose the red line, which corresponds to these intrinsic weights, I often get a better approximation than many other different weights that can be considered that are both smaller and larger. So in some sense, this is an example of the fact that this is the optimal type of weighting scheme to do smooth function recovery with compressed sensing. And so by exploiting the structure of the function, we can get better approximations from fewer samples than required by, say, unweighted schemes or other weighting choices. Okay, so the problem with all of this so far is that it applies only to the recovery of real or complex vectors x. So of course, one of the things that I was working on during my PhD with Clayton was to answer the question, can compressed sensing find sparse approximations to solutions of parameterized PDE, where the parameter solution map y maps to u of y is Hilbert-valued, and so we have v is equal to h01 in this example. And the idea is that we don't want to just recover some functional of the solution. We want the actual entire solution. We want to approximate it in a fully discrete way. So one approach to this, of course, is we could do pointwise reconstruction. So we could choose a mesh of nodes xi up to some kh, a subset of our physical domain. And then at each fixed point xi, we could solve an L1 minimization problem. So minimize over z and cn. The one norm of Z subject to AZ minus BI as 2 norm is less than or equal to eta, with B is before and now, or sorry, A is before and B, I is now the solution fixed at the point xi, and in each component evaluated at the random data yj. So we can interpolate these solutions to get a fully discrete approximation u lambda h hat, which is the sum over nu and lambda, sum I equals 1 up to k sub h. Kh is the number of degrees in our finite element basis. The c nu of xi's are the pointwise approximations that we get back from this approach. And the challenge here is that it's unclear how to actually show error estimates for the resulting PDE approximation if you do this. So of course, this is just interpolating these solutions to this L1 problem in a finite element basis, but I don't know how to show global error estimates from this. So what we did instead was we considered a simultaneous reconstruction problem. So we introduced simultaneous compressed sensing Hilbert-valued recovery. So here we consider a Hilbert-valued vector C and Vn. And that means just that in each component of the vector, the component is not a scalar value like a real or complex value, but actually an element of a Hilbert space V. With the concept of a Hilbert-valued vector, you can define matrix vector products in the same way that you would do for standard vectors. So here you have A, the measurement matrix, and C, our Hilbert-valued vector. And then in the ith component, the product AC, this is equal to the sum from j equals 1 up to n, aij times cj, which will itself be an element of V if we haven't introduced any discretization. And then so we say that Z in Vn is S sparse if all but S of its components are identically equal to 0. And given a norm on Vn, we can define the error with respect to, that norm error of the best S term approximation to Z. So basically the best S term error with respect to that norm in the standard way. So we take the infimum of the norm Z minus X such that X is S sparse for a vector Z. And then we say that the vector Z is compressible with respect to this norm if sigma sub S goes to 0 quickly as S increases. Of course, in practice, we're going to discretize. So we want to replace V with VH, for example, with the finite element methods. And therefore, the error analysis for any recovery scheme with this setup is going to have to account for that discretization error at some point. The question is, which norm should we use? And the natural choice from the PDE is if you have, so for two vectors Z and Z prime and Vn, and the weight vector W nu with components greater than 0 and P and 0 to 2, we can define these weighted PWV norms, which are defined as the sum over nu and lambda, the weights W nu to the 2 minus P times the coefficients Z nu of my Hilbert-valued vector, evaluated in the V norm to the power P, and then we take the 1 over Pth power of the result. And we can also define an inner product. So here we have Z and Z prime, and the two semicolon V inner product is the sum of the inner products in each coordinate of my Hilbert-valued vector. So for P greater than or equal to 1, this space with this norm is a Banach space, and with P equal to 2, we actually get a Hilbert space. With the compressed sensing approach in mind, we can reformulate the weighted quadratically constrained basis pursuit problem to a V-valued version. So we're just going to replace the norm with the scalar valued norm here with this Hilbert-valued norm in both parts. And then we can, of course, show things like uniform recovery by considering a modification of the RIP. So here we have the VW RIP. So we're going to consider weighted KW sparse vectors. And then, of course, the V RIP looks very similar to the standard RIP. It's just got different constants here and different norms. And then this proposition says that A satisfies the weighted RIP if and only if A satisfies the V weighted RIP. So suppose that V is a separable Hilbert space and the matrix A satisfies the weighted RIP with KW weighted restricted isometry constant delta KW. then A satisfies the VRIP with VW restricted isometry constant delta KW V equal to delta KW. So in other words, the same sample complexity requirements that we're going to show for the for this problem will be inherited from the standard weighted L1 problem. And of course, like I said, we're also interested in this noisy recovery settings. We have some noise in our data, in our measurements, which could, of course, come from the PDE solve itself. So we're going to consider this weighted V square root lasso problem instead of the quadratically constrained basis pursuit problem, in particular because I don't have to actually know anything about the noise level to set this parameter lambda. So this is called a noise blind recovery scheme. And just to remind you, these are the ingredients that I have for this weighted Hilbert-valued approximation. So first I have the normalized measurement matrix and the measurement vectors, B, and then I have the error and truncation vectors, E and E prime. The linear system I'm trying to solve is this system with these E and E prime. Excuse me. I'm going to use the intrinsic weights and the hyperbolic cross as discussed. But the remaining problem now is how do we actually solve this V-valued weighted square root lasso problem? And the way we're going to do that is actually using so-called primal-dual iterations. So here, this is the problem that we're trying to solve, minimize over Z and Vn, G of Z plus H of AZ, where G of Z is equal to the lambda times the 1W V norm of Z, and H of Y is equal to Y minus B, and the 2B norm, so that when I substitute AZ, I get AZ minus B here. Of course, I can define the convex conjugate of H in the standard way. And then the Fenchel-Rockefeller dual problem is minimize over C in Vm now, G star of A star C plus H star of minus C. So the Lagrangian here is going to be L of Z C is equal to G of Z plus A Z C in the Vm inner product minus H star of C for Z in the domain of G and C in the domain of H star. The primal dual iterations are given some initial points x naught and c naught. We're going to define the sequence of iterations from 1 to infinity by Zn plus 1 is this proximal map with respect to tau G of Zn minus tau times A Cn, A star Cn, and then Cn plus 1 is the proximal map with respect to sigma H star of Cn plus sigma times A 2 times Zn plus 1 minus Zn. So we're over relaxing in this Cn for some nice convergence properties, and the proximal maps are defined here in the standard way. So we are also going to focus on computing the ergonic sequence for this update. So here, Zn plus 1 bar is equal to n over n plus 1 times Zn bar plus 1 over n plus 1 times Zn plus 1. And this is nice because this will help reduce some of the variance in the iterations of the primal dual iteration. The thing that's going to actually get us to the exponential convergence rates, though, is going to be this efficient restarting procedure, which is going to lead to exponential convergence, and some information can be found in these two papers here on the restarting procedure. So I put all these ingredients together. I have D is the dimension of our problem. F satisfies the holomorphy assumption. M is greater than or equal to 3. K is greater than or equal to 1. And epsilon is between 0 and 1. Then for every t greater than or equal to 1 and zeta less than or equal to zeta prime, there exists an algorithm that computes an approximation f hat from m samples satisfying the following. So if I look at the error in the Bachner norm between f and f hat, this is going to be less than or equal to zeta plus zeta prime plus e to the minus t for any gamma between 0 and d plus 1 inverse times d factorial times the product of the log of the rho j's, where the rho j's here are the widths of the Bernstein ellipses from before. And zeta is going to equal to the error, the approximation, plus the sampling, plus the discretization. And so, of course, these have explicit forms here. This is the error, the approximation. quantifies how well f is approximated by polynomials, and it's exponential, sub-exponential, and m. Here, this is the error of the sampling. So this quantifies the error in the pointwise evaluations that we have. And then we have the error in the discretization. So since we're working with VH instead of V, we have to account for the discretization error as well. And the main takeaway is that the cost for this proposed primal-dual iteration for solving parametric PDE or approximating a generic Hilbert-valued function is algebraic and m, the number of samples for fixed d. And so it looks like order t times m to the alpha plus 2 times log m to the d minus 1 times alpha plus 1 as m goes to infinity. So for more details, you can see our recent paper on this. Now let's look at a couple of experiments. So here, considering compressed sensing using Legendre polynomials, I have m points drawn randomly and independently from the uniform measure. I have a hyperbolic cross. This is a two-dimensional benchmark problem. And I choose the index of the hyperbolic cross to be 184, and the cardinality of the hyperbolic cross that I result with is 997. Solving the parametric elliptic problem, here I've got the coefficient is explicitly given by this very simple 5 plus e to the x1 times y1 plus x2 times y2. This is just a benchmark for our algorithm, basically to verify that everything is working well. So here I've got on the left, this is the convergence with respect to the iterations of the primal-dual algorithm. In particular, the ergonic sequence error in the L2, in this Bachner norm error. So the primal-dual iterations without restarting, that's the dashed line here. You can see it decays very, very slowly with respect to number of iterations. But these different colored lines here, these all correspond to the primal-dual iterations when I set this zeta prime from the previous theorem to different values. So the main takeaway here is that while the theorem suggests that there should be that we have this relationship between zeta and zeta prime to get the error, in practice we actually don't really see this. This zeta prime value can be set arbitrarily small. We still get recovery. So this is more of an artifact of the analysis than it is an actual practical limitation of the algorithm. So in other words, we can set this value very small and get very good recovery of this solution, this benchmark problem. And in particular, the rate that we see of convergence for the algorithm with respect to the iterations matches what we'd expect from the theory, which is this dotted line, e to the minus ct, where c is a constant we compute in the paper. Also on the right here, I've got the convergence with respect to the number of samples used in training. And this plot here is averaged over 50 trials. So here you can see that we're getting really good approximation to this very simple benchmark problem. This is a little bit more challenging problem. So this is 30 dimensions. Here I set the index for the hyperbolic cross to be 10, and the cardinality of the hyperbolic cross is 7,841. Here you can see that we're really running into the error of the problem, the noise of the problem, the truncation error. This is, like I said, a more challenging problem. You can see the coefficient down here. And in particular, when we look at the convergence with respect to the number of samples, we're only able to get a maybe about 10 to the minus 2 error for this problem. Okay, so the remainder of my talk, I'm going to talk about deep learning. So this method for polynomial approximation is great, but there are many problems where we don't actually have all of the assumptions that we may want to work with when applying polynomials, for example, smoothness. And in fact, we may actually have something more discontinuous or more difficult to approximate. And deep learning, over the last decade, we've seen some pretty impressive results over a variety of historically challenging applications. But the broad question that we had when we started this work was, should these techniques actually be used in computational science? So here, the architecture of the neural network that I'm considering is, here I've got an input dimension D in the first layer, output dimension N in the last layer. The depth is L, and the widths of each layer are going to be N sub L. We'll define N as the maximum of these later on. And then the component-wise activation function sigma is used to construct the network. For example, we could take sigma as the ReLU function. And then we have these affine maps AL from RNL minus 1 to NL of the form X maps to WL X plus BL, where these are the weights and biases of the network. The network function that's computed by the deep neural network is given by these compositions AL plus 1 with sigma with AL repeated in this way. So this is the neural network that we're going to consider a fully connected feed-forward deep neural network with an activation function sigma. Classical existence theory says that the single layer networks approximate Lipschitz functions with order 1 over n error on bounded intervals. We also have the universal approximation theorem for continuous functions. Modern existence theory has significantly improved on these results and now consider a wide class of functions that are efficiently approximated by neural networks, including holomorphic functions, piecewise Helder functions, and functions belonging to PDE spaces and Sobolev spaces and Besov spaces. The DNN holomorphic function approximation problem in particular, we're going to focus on this. The results that have been established so far say that neural networks can match the optimal polynomial approximation rates. In other words, deep neural networks achieve best S-term rates with size and depth bounded in terms of S and D, and convergence rates on the order of e to the minus gamma times S to the 1 over D, where gamma depends on the region of holomorphy of the function. The problem here is, though, that existence theory says very little about practical performance. So the big questions we had were, one, can these DNNs be obtained by training? And if so, how? Two, are these if these DNNs are trainable, what is the sample complexity of training them? So how many samples do I actually need? Is it proportional to that of current best-in-class polynomial schemes based on compressed sensing? Can these methods perform well on problems where polynomial approximation is known to perform badly? So for example, discontinuities or non-axis aligned functions. And are deep neural networks measurably better than shallow networks at function approximation? And then finally, do standard methods of training actually achieve these polynomial rates? So it's one thing to be able to say that they can approximate them in theory, but is it actually achievable today given the hardware and software limitations that we have? So the following theorem answers questions 1 and 2 in the affirmative, and it says that this is part of my work, beginning of my work with Ben. It says that there exists a training procedure based on minimizing a regularized L2 loss function for which there are minimizers that perform as well up to a constant as compressed sensing for high dimensional polynomial approximation with respect to the accuracy and sample complexity. So the idea here is that we initialize the deep neural network to approximate polynomials, and the training problem solves the compressed sensing problem. So in other words, we're going to replace the polynomial basis with something predicted by the neural network and use that instead for compressed sensing problem. But since we can approximate these polynomials to arbitrary accuracy, it turns out that it actually implies that we can get the accuracy and sample complexity result. So the procedure is actually not expected to produce a deep neural network that performs any better than compressed sensing. All we're doing is emulating that problem. And it differs from the standard L2 cost function typically used and requires a non-standard initialization to achieve this. For the other 3 remaining questions, we conducted rigorous numerical experiments. You can see here the details about the implementation, and I'll describe just the bare details here in the problem. So here we're given these random measurements. We want to approximate the function f, and then we have these fully connected ReLU deep neural networks, and we're going to compare this with compressed sensing. These are some more details about the runs. If we do this just approximating a very simple function, say log of sine of 100y plus 2 plus sine of 10y, here's what it looks like if I take ReLU networks with 2 hidden layers and 20 nodes on each hidden layer and try to approximate this function in the standard way, minimizing the L2 loss function with the atom optimizer. This is what I get when I do this 20 times. These are each correspond to a different trial of running that problem. And this corresponds to the black line here, if you're interested on the right. No, sorry, the blue line. This is the 2 by 20s. But if I keep increasing this and say now this is a 4 by 40, This corresponds to this yellow line now. Yellow is further down than blue. We're increasing the accuracy here by increasing the depth and the width at the same time. 5 by 50, now we're down to this purple line, 10 by 100, and 20 by 200. Now we're actually matching the error of the compressed sensing approximations in this one-dimensional problem with these ReLU deep neural networks. However, if we continue to add more layers and more nodes per layer, eventually we get to these problems where this in particular is caused by the initialization, but it highlights the fact that for this type of approximation, there's many variables that need to be tuned, and in particular, if you're not careful, you can end up with a very bad approximation. So this is a very careful training problem that we have to consider. And then we did these experiments where we looked at the average error over 20 trials, comparing the L1 minimization with the ReLU networks. And you can see here that for very smooth function approximation problems, there's this huge gap between what we can do with the networks and what we can do with compressed sensing. I'm going to skip some of these experiments because I realize I'm close on time. Maybe I'll just highlight that this is a less smooth function approximation problem. We can see that the neural networks actually outperform compressed sensing for this problem. And here we've chosen the basis so that we could get as high accuracy as we could afford with the budget that we had for compressed sensing, but the neural networks outperform it within, say, after about 1,000 samples. And this is a discontinuous function approximation problem. So here we're approximating the indicator of this jump of this set K here on the right. And you can see the compressed sensing approximations don't actually converge on this problem, but neural networks are able to get at least some accuracy on this discontinuous function approximation. So there's a large gap between theoretical results on expressive power and practical performance. I'll say that performance is comparatively worse on functions which are well approximated by compressed sensing and polynomials, but outperforms compressed sensing and polynomials on discontinuous or highly anisotropic functions or less regular functions. And sometimes deeper and sufficiently wide neural networks perform better. Of course, this is function dependent. Point one I'll mention, has recently been investigated by Gross and Voigtlander, where they show that current algorithms are not actually capable of realizing such rates. And you should see their paper on the proof of the theory to practice gap in deep learning referenced here. Depending to the organizers, do I have time to continue or should I wrap up here? Because I have some more results I could show on parametric PDEs, but I think the main message has already been delivered.
I mean, we do have, let's say, 15 minutes, 10, 15 minutes. So if you can go ahead a few more minutes, maybe 5, and then we open the floor for questions.
Okay, sounds good. Okay, so let me just continue then. So here now we're going to change to the problem of approximating a parametric PDE with the deep neural network. So the main thing that changes here is, of course, now the architecture of the neural network is not just outputting a single scalar value, but in the setup that we define here, we're actually going to output the values of the coefficients of the finite element expansion of our function with the neural network. So here, this phi y of k is going to be the output of our network. Sorry, k sub h is again here the dimension of or the cardinality of the finite element approximation. And the testing data, the training data, we're gonna give again the same thing. The samples and the function approximation values. And we're going to minimize here now the difference between the true coefficients obtained for each sample value yi via finite elements and the values predicted by the neural network. So this is going to be our mean square error loss, and we're going to consider minimizing this in training to get an approximation to the parametric PDE. So again, here, this is the setup. We have random measurements, yi and bi. We're approximating the forward map y maps to f of y in v. So we're using the finite element method implemented by the Phoenix project here, fully connected TANH, ReLU, and leaky ReLU deep neural networks, and comparing this with this compressed sensing-based approach from the first half of the talk. Here's some more details about the training, if you're interested. And the testing, of course, here we're using higher order sparse grid quadrature to do the testing so that we can compute these approximations to the Bachner norm errors. So again, this is the benchmark problem. Here's the coefficient that we're considering. It's just a simple affine function of x and y. And now we're going to approximate f from our sample data. So on the left here, this is the prediction for the solution obtained by the neural network from a tan h 5 by 50 deep neural network at a particular y value in the input after only 2 epochs of Adam. So it looks quite bad. And then on the right, this is the reference finite element solution. Here's after 2045 epochs of Adam, we get down to 10 to the minus 7 order mean square error with the MSE defined on the previous slides. And that matches now quite well with the reference finite element solution to this problem. Here's a more challenging 30-dimensional example. This is the same parametric diffusion equation with the log affine diffusion coefficient from several slides back. And here, this is, I apologize, there's so many lines on this plot, but the main idea is that the solid line here, this is our Legendre hyperbolic cross L1 minimization approximation, so our compressed sensing solution. And then all of these lines here that are below it, these are all tan H networks that outperformed the L1 minimization procedure on this challenging 30-dimensional test problem. The main conclusion here that we have is that by tuning the not necessarily theory-based architectures and training, we're able to match or outperform the state-of-the-art methods in this study. And we plot these in 2 different errors here. You can see this is the L2 Bachner norm error, and this is the H01 Bachner norm error. The final theoretical result I'll present is this practical existence theorem that says that this is from our paper in from this MSML conference from 2021. It says that there exists a deep neural network architecture of a given size and depth depending on M and D, and a training procedure, for example, a loss function, a regularized loss function, such that any minimizer of the corresponding loss function minimization problem actually approximates f up to an explicit error bound, and the error is split into 3 key terms that fully describe the effects of all main errors involved, including the approximation error, a measurement error, and a physical discretization error. So as in the scalar case, the procedure outlined in this result is not expected to yield superior performance over compressed sensing. And this result holds for generic Hilbert-valued function approximation, not just PDEs. I suppose I could end here. Some future work that we're involved in is continuing to work on compressed sensing based approximation of solutions to parameterized PDEs. So extending the CS analysis to the Bonnick-valued case, and extending algorithms and convergence to handle Bonnick-valued data. And then some possible avenues for improving practical DNN performance include better architectures and training procedures. So for example, exploiting sparsity or inspired by compressed sensing that help DNNs achieve theoretical convergence rates in practice. And then if I have time, I'll mention one brief thing. Something we've been working on in particular recently is improved sampling strategies for DNNs that are motivated by polynomial approximation to increase performance. And so here, the main idea is that we're going to consider adaptive sampling schemes based on the Christoffel function. But here, instead of a polynomial basis, we're going to consider the output layer or the penultimate layer nodes as a dictionary of functions and define a sampling measure with respect to that dictionary in the Christoffel function. And just very briefly, if we do this, we get a sequence of sampling measures mu j, and we can alternate training the dictionary and updating the discrete sampling measures based on previously sampled points to get a better approximation. So here's a function, smooth function, and here we can observe that doing this with the tan H activation leads to a substantial decrease in the error, whereas for ReLU activations, we don't actually observe that, which is kind of interesting. But for other smooth activations, we've observed this as well, that adaptive sampling schemes can help mitigate these challenges with deep neural networks. So here are some references from my talk, and I'll end here.